So our goal today is to compare two functions to determine which function is growing faster. And we're going to be using limits to do that. This chapter 9 is all about limits, and next next section is indefinite integrals, where we have to do limits with our integrals. So we will be using limits to compare our two functions. And when we go about comparing our functions, we're only comparing functions that are positive as x approaches infinity. So we're only comparing functions that are getting bigger in the positive direction. It can start out negative. The sign starts out negative, but as we go towards positive infinity, it's in the positive direction. It's going up, not down. Yes. So we have three graphs here. Any ideas as to what they actually are? Y equals x is the red graph.
And the natural log and then the exponential.
E to the x is the blue graph. And ln x. Which one looks like it's growing faster? Getting bigger, faster. E to the x. Which one looks to be going the slowest? Natural log. So e to the x, just looking at the graph, is faster. And that makes sense because exponential functions are all about getting big really fast.
With one.
And ln x is slower, which makes sense because it's the inverse of e to the x. So when we compare our functions, we've just compared them looking at the picture, but the picture isn't always enough information. We're going to learn how to compare them algebraically. So again, we need this information that they're positive, so suppose f of x is greater than 0 as x approaches infinity. So it doesn't have to be positive all the time, just as we're going to positive infinity. G of x is positive as x approaches positive infinity. Then we have a couple of possibilities. If we take the limits of the two functions divided together, and it comes out as infinity, then f of x is faster. I think my comma should have been before the then. It's growing faster. So let's see if that makes sense. Let's say looking at this, we're going to have f of x be e to the x. We're going to have g of x be x. So this is just for us to think about it. You don't have to write it down if you don't want to. As x approaches infinity. So if I start plugging in bigger and bigger numbers, if we go e to the 1 over 1, yeah, e's bigger than 1, 2.7, bigger than 1. Well, let's pick something even bigger. Let's say 10. What's e to the 10? Oh. I don't know, e to the 10 is a calculator.
27.1.
That's not what I got. I got 22,026.5.
It was a good guess.
Okay. 22,000.
Congrats.
Okay.
And 26.
So 22,000-ish over 10.
At first it gave me e to the 10th back, and I was just like, thanks.
What's 22,000-ish over 10?
A lot.
Still a lot. What if we go even further? What if I do e to the 100?
Then it's still a lot.
That's even more. That's gonna probably get into scientific notation.
Let me try. It's 2.68 times 10 to the
10 to the 43rd. That's 43 places. 44 if you count the first digit. So we have a giant number divided by 100. What's a giant number divided by 100? A slightly smaller giant number. So what pattern is happening?
It's getting exponentially bigger.
The exponential is outpacing x so quickly, x isn't even touching e to the x when we're dividing. The dividing is basically negligible. We're taking big numbers, dividing by pretty small numbers, and we're still getting really big numbers. So does it make sense that we'd hit infinity? If we have a really, really big number divided by a
Really, really small number.
not even really, really small, but if we go e to a million over a million, even though we consider a million a big number,
Yeah.
e to 1 million is so big,
That it,
1 million doesn't touch it. Dividing by 1 million doesn't do a thing. So,
It's infinity.
is that what it's saying?
Yeah.
It comes up with the infinity sign.
yeah, e to the million, our calculator can't even calculate it at that point. It's too much information for our calculator. So, since this top function got big so fast, the bottom function didn't even touch it, which means the top function is growing faster. It is a faster function. Well, let's say we divide and we get 0. Let's say we divide f by g and we get 0 instead of infinity. How do you think we're going to get 0 instead of infinity? Let's look at our limit as x approaches infinity of e to the x over x. What could I do to this so that I get 0 instead of infinity? Okay. Put infinity on the bottom. If I put x over e to the x, is that going to come out as 0? Again, I'm going to have 10 divided by e to the 10th. That was 22,000. Small number divided by a pretty big number. Pretty small. Getting closer to 0. If I do 100 divided by e to the 100, getting even smaller. If you plugged in a million over e to a million, it'd probably just pop out 0 because your calculator can't put in enough decimal places.
Wait, what do you want?
A million divided by e to a million.
I'm working on it. If I don't count it out, I will always miss one.
So which function is bigger though? Which one's growing faster when we have this setup? The bottom. So then,
It comes up as 0 point, and then nothing after it.
so it knows there's actual decimal places, but it can't calculate them. So
Wait, what is it?
It's a 0 and then.
Oh, yeah.
okay, so g of x is growing faster. And the reason we need this is because we're not necessarily going to know which function is growing faster. So we need to know what happens. What if we put the faster function on top? It's going to come out as infinity. If we put the faster function on bottom, it's going to come out as 0. So then we can identify, oh, the faster function was the one I put on the bottom. And then our last option, let's say we have f of x over g of x equals L, some number as our limit. Sorry, I think I put my comma in the wrong spot. Should have been comma then.
I actually don't think so. I think it's
I
Really?
then. Yeah, because you say then and you pause and you say the rest.
I think
It's hard to tell where it's math instead of like a sentence.
English teacher here, but you should just write it out.
Okay. So what's going to happen if we hit a number instead of infinity or 0?
then they're growing the same.
you're growing at the same rate. So let's try a problem. Let's say we want to compare the growth rates of 10x and x. Did everyone get the number 3 before I scroll over? So let's look at this two ways. Let's look at the graph first and decide what we think will happen, and then try it algebraically. So graphically, what are the graphs of 10x and x going to look like? X is just the diagonal line. What's 10x going to look like?
Skinnier.
Steeper.
Steeper.
Yeah, skinnier as in probably closer to the y-axis is what you
Yeah.
say. Okay, so just looking at the picture, what do you think is going to happen when we solve this algebraically? Well, it depends on which one do you think is faster, 10x or x? Or do you think they grow at the same rate? Okay, so let's try that algebraically and see if our hypothesis is correct. We say the limit as x approaches infinity. And then I can pick any order. Do you want to do 10x on the top or 10x on the bottom?
10x on the top.
Okay, 10x on the top.
So it doesn't matter what order you put on it?
Nope, because if you put them with the steeper one on top, it comes out infinity. If you put it with the steeper one on bottom, it comes out 0. So we just have to know what the answer means.
What you want.
Yeah. So I need to find this limit. We could do L'Hopital's rule, or what can we do? Well, infinity over infinity.
Oh yeah.
We can cancel out stuff. What can we cancel out?
The x's.
The x's. So we would get the limit as x approaches infinity of 10, which is 10. That did not meet our expectations. We thought 10x is going to be faster than x. So why is that? Graphically, 10x is getting bigger faster. So we need to know, what do we mean by faster? Mathematically, what do we mean by faster? So that's why I even wanted to do this problem. I was looking at it, I'm like, why isn't 10x faster? It should be faster. Picture is faster. So let's look at the 10x, the x, and e to the x. Again, let's plug in some numbers. So let's start with 10, something small. If I plug in 10 for x, what do we get?
10.
10. If I plug in 10 into 10x, 100. And e to the 10th we said was 22,000-ish. Okay. So we have 10, 100, 22,000-ish.
Yeah.
We don't even care what it is. So what are we noticing about those three numbers? They progressively get bigger, but how much bigger than 10 is 100? 90. How much bigger than 100 is 22,000?
21,000.
A lot. 21,900, and that's us just approximating. It's a lot bigger. It's not even just a tiny bit bigger. It's a ton bigger. Well, let's take this up a notch. Let's say 100. 100 times 10 is 1,000. What was e to the 100? Sorry, I don't remember it anymore.
We didn't do that one.
We didn't do that one? Okay. What's e to the 100?
2.6881 times 10 to the 43rd.
Oh, no, we did that one. I remember 10 to the 43rd.
Third.
Point third.
Okay. So again, they get progressively bigger, but what's our difference between 100 and 1,000? 900. What's our difference between 1,000 and 2.688 times 10 to the 43rd?
43rd.
A lot.
A lot. If I subtract 1,000 from this, is it going to make a difference?
No.
Is it going to even make a dent in this number?
No.
But if I subtract 100 from 1,000, is that going to make a dent in that number? Not a huge dent, but still, it will make a dent. And this one, it doesn't make a dent at all. So when we're talking about a function growing faster, we're saying it's growing so much faster than the other function that the other function can't even touch it. The other function isn't even close or anywhere near it. So it's growing at such a faster rate. So we consider 10x and x to be growing at the same rate because 10x isn't growing so much faster that it doesn't make any difference when we consider x with it. Especially if we're doing division. How does 1,000 divided by 100 affect 1,000? Takes it all the way down to 10? 10. That made a big impact. But if we do 2 times 2.688 times 10 to the 43rd divided by 1,000, still. Yeah, maybe a tiny bit, but not much. So we do consider, so that means any polynomial that's the same degree grows at the same rate. I could have 5,000x plus 2. We still consider it growing the same rate as x because it's not growing big enough, fast enough. Okay, so I want you guys to try this one. We have e to the x and x squared. Which one do you expect to grow faster? We have an exponential and we have a polynomial. Exponential. Probably going to be exponential. So, I want you guys to try this one. You have to put in the limit on your own. You're applying the limit to check it, so you know you're going to do limit as x approaches infinity, and then you have to decide how you're going to stack the functions. Okay, so it looked like most of you chose to do e to the x over x squared. You could have done x squared over e to the x and you would just get 0 instead. We have e to the x over x squared. What did you end up having to use? L'Hopital's rule. When we go through the whole L'Hopital's process, we get infinity. And then you have to make your conclusion. What can you conclude because our answer came out infinity?
That e of x is growing faster.
E of x grows faster.
Oh yeah, e to the x.
So our conclusion is not the answer to the limit. That is not the answer to this problem. It's which function is growing faster, because they didn't ask us just to find the limit. We're using that as a tool to make a conclusion about which function grows faster. So we also have something called the transitivity of growth rates. Do any of you guys remember the transitive property from geometry?
Oh my gosh.
If A equals B and B equals C,
A equals C.
A equals C.
Remember when we had to write proofs?
Proofs are only useful if you're going to actually go into mathematics itself.
What do we need? Geometry spent like an entire semester on that. So entire semester was like a year.
Yeah.
So upset now. I hate them.
So if F is the same rate as G and G is the same rate as H, then F is the same rate as H. So the reason we need this is because sometimes when we try to compare two functions as they are, we don't get very far. And we'll see that in this example here. If we try to compare the two functions, square root of x squared plus 5, and divide that by 2 square root of x minus 1 squared, when we try and go through and apply L'Hopital's rule, we can apply it, but we'd be applying it forever. So I want to show what happens when we try and apply L'Hopital's rule, but you don't necessarily have to write it down because it's not how we're going to actually solve the problem. It's one way you might try and fail and be like, oh, I've got to try something else, which happens a lot in math. A lot of times you try, you fail, you're like, well, that didn't work, what else can I try? So if I tried doing this the normal way and just said limit as x approaches infinity of square root of x squared plus 5 over 2 times square root of infinity minus 1, 2 times square root of x minus 1 all squared. What's going to happen when we plug in infinity?
What's the square root of?
That is a good question. I asked myself that question as well, and I was like, well, I'm not sure. But I'm going to assume the square root of infinity is infinity. What does your calculator say?
Good question.
So assuming that top one is infinity, and assuming the bottom one is infinity,
It's infinity.
it's infinity? Okay. I kind of assumed it. Then we can apply L'Hopital's rule. But when we apply L'Hopital's rule, what's going to happen? I have to do chain rule.
Ugh.
So we apply L'Hopital's rule. We get 1/2 times x squared plus 5 to the negative 1/2 times 2x over 2 times 2 square root x minus 1 to the first, technically, even though we don't have to write to the first n, times the derivative of the inside. Derivative of 2 times square root x is 2 times 1/2 x to the negative 1/2. And why didn't I care about the derivative of minus 1? It's 0, so plus 0 doesn't change anything.
2 times 1/2, could we use that as 1?
One.
Yes, you
Yeah.
could. We could get rid of that and just leave it as 1. So now that we look at it, what's going to cancel? That's what we usually bank on with L'Hopital's rule, is something's going to cancel so that we can... Nothing will cancel.
Okay, I was like, either I'm going crazy.
Nothing will cancel. We might be able to do some rearranging. I could bring x to the first up, or x to the 1/2 up top. This x squared plus 5 to the 1/2 on the bottom. But what's going to happen when I plug in infinity again?
Infinity over infinity.
Infinity over infinity. Then we're going to have to do product rule. Is this ever going to get any smaller? Stuff is not going to disappear.
Oh,
So-
so if you're irritated in a class, you give them this problem. Like, okay, do this.
So we say, that didn't work. This is not going to work the way we're trying it. So instead, I'm going to pick a third function to compare these functions to. So I'm going to pick a function. I'm going to pick my h of x.
7.
Now we can't just pick any function, okay? Because otherwise it might not prove anything for us. But that transitive property only worked when something grew at the same rate. So our goal is to pick something that we think will grow at the same rate as square root of x squared plus 5. So the way to figure out what function would be best to pick, let's pretend we don't have anything but the basics. We want the highest exponent, so the highest degree term, and we want like the square root that's involved. So I'm going to ignore plus 5. And if there was a plus x plus 5, I'd ignore the plus x plus 5. I'm going to just look at square root of x squared. What function is the same as square root of x squared?
X.
X. So I'm going to pick h of x to equal x. And we're going to see, and sometimes with this, again, maybe we're going to pick the wrong function and we're going to have to try picking another one. So we're going to pick x and we're going to compare f of x to x and g of x to x. So we're going to compare limit as x approaches infinity of f of x, which was square root of x squared plus 5 over x. And again, I could flip that. I could put x over square root of x squared plus 5. And I'm going to pick, or I'm going to use g of x as well. We're doing two different limits. It was 2 square root of x minus 1 squared. Yes. Sorry, I know what I'm supposed to do next. I just thought of something else that you may also have as a question. And I'm not sure what the answer is to that. So I'm wondering why we don't just go ahead and do L'Hopital's rule right now. Because that's not how they did it in the book. If I were a student, I'd say, hey, I plug in infinity, I get infinity over infinity. Do L'Hopital's rule. So let's experiment for a second. See if L'Hopital's would work and get us the same answer as the book. If not, I'll show you the way the book. So don't write this down because it may not work. We're experimenting because if I were you guys, that's what I would be like, hey, L'Hopital's rule. Go right ahead. So L'Hopital's rule, we have 1/2 x squared plus 5 to the negative 1/2 times 2x over 1. But rearranging things, we would get x over x squared plus 5 to the 1/2. I think I see what's going to happen.
I don't.
It's going to just keep flipping back and forth forever. That's why we can't keep doing L'Hopital's rule. If I do L'Hopital's rule again, I would get 1 over 1/2 x squared plus 5 to the negative 1/2 times 2x. So then I just get back to what I had originally, x squared plus 5 to the 1/2 over x. And it would just keep flipping back and forth forever. Okay, answered my question. So, do you see the pattern that's happening? You see that we got back to what we had at the very beginning? Yep, so L'Hopital's rule didn't actually work with this one, but there is a slick trick we can use. So we're going to have to do some finagling again.
Oh, I get it, finagling.
Okay. So I want to get rid of this and not have it be a fraction anymore. But I can't just bring random stuff into square roots. What's the only thing I can bring inside a square root?
Positives.
Another square root. I can multiply 2 square roots together. I can divide 2 square roots together. So I want this to actually be a square root. Problem. I can't just make it a square root because I want it to be. So what can I do to undo that?
Square it.
Square it. This is another clever form of one-ish. Oh, okay. I did something, but I undid it so that I didn't really do anything. But now that this is a square root,
Poor x. It's been squared and square rooted.
I can actually divide this x squared inside the square root. I can combine it all together and have x squared plus 5 over x squared. So, I can actually divide x squared into each of these. Gives me 1 plus 5 over x squared. And what's going to happen now when I plug in infinity?
It'll be 0.
5 over x squared, well 5 over infinity squared will become 0. So we'd have 1 plus 5 over infinity squared. That goes to 0, so we really get 1.
You're so excited. Makes me happy.
So what conclusion can we make about f of x and h of x? Because we need to make a conclusion.
They're
1 is
equal.
not our answer. Close.
Almost equal.
Not they are equal, but they. What have all our conclusions been about?
They have the same.
They grow at the same rate.
You know? So their rates are equal.
Yes, that's why I said kind of. So now we're going to have to use a similar slick trick for the other one. Sorry, that was a horrible T.
Well, for you, Mew. Find it ironic that you were the one that said that. All these years you've been bugging me, right? As in, like,
These months. Okay, so let's look at the other one. I'm going to have to use a similar trick. What am I going to have to do for this one? What's our main, before the main thing was the square root, what's our main thing affecting this? Squared. Again, squared. I can't bring something into squared unless I also have something that is squared. So we square it, but to undo that, we square root it.
so it's kind of the opposite of what you did last time. Like it's the same with the square root. It's on the inside.
Yeah. It's kind of the same, but kind of the opposite. And then we do the same thing. I can combine this to be 2 square root of x minus 1 all over square root of x squared. We're doing our properties of exponents backwards. We're used to taking this and distributing the square to the top and to the bottom. We're undoing that now. And then I want you guys to finish this, because you're going to finish it the exact same way. You're going to divide square root of x into both. You're going to see what happens when you plug in infinity. So I want you guys to finish this problem.
Oh, I heard a pigeon.
So we divide in, we get 2 minus 1 over square root of x. We plug in infinity squared. What happens when we plug in infinity?
It's 2 minus 0.
2 minus 0, 2 squared is 4. Now, did it matter that our limits did not match? No, because they still have the same conclusion. F of x and h of x grew at the same rate. This time g of x and h of x grew at the same rate. So now we need to apply that transitive property. What can we conclude from these two conclusions? F of x and g of x grow at the same rate. Okay, so I don't think we've done an EOO before. Do you guys know what I mean by EOO? Every other odd. Every 4 problems. So you're going to do 1, 5, 9, 13.
Thought it was to 100. I'm like,
No, it's really only 10 problems total.